So we've talked about in general chemistry, we identified isomers in terms of individual atoms, elements. If you have the same number of protons, a different number of neutrons, that's an isomer. Organic chemistry approaches it a little different. Isomerism is it identifies the relationship among the different atoms in a molecule, how they're arranged, because that arrangement can radically affect the outcome of a reaction. That's the umbrella for studying isomerism. And this hierarchy it's accurate if we have the same formula. One good example here is, let me see. I'm going to have to draw the molecules before I can do the molecular formula. If we have this molecule, COH, that's ethanol, right? We have this molecule, should have the same molecular formula. Let's see, C2H6. Yep. And O. So it's got the same molecular formula, but different structure. This is, let's see, what does your author call it? Or what does Carty call it? Constitutional isomer. The magic word here is connectivity. How are the atoms connected? In these two, they're obviously connected differently. All right, we just moved that oxygen over here and put the hydrogen with that carbon. It's a different kind of connectivity. These are, sometimes they're called, in this case, constitutional isomers. Sometimes they're called structural isomers. Or structural or constitutional isomers. And these obviously have different physical and chemical properties. Right? This one is going to be somewhat polar with a hydrogen bond available. This one's going to be nonpolar. So they're radically different and easy to separate because of that fact. However, if the connectivity is the same, then we have the possibility for stereoisomers. And now that's where we're going to focus our attention. These guys are easy, right? You just look at the way the structure is written. But if we have something like this, let's see. Let's say a hydrogen there, and let's put a bromine here in the plane of the board. And then let's bring out the front chlorine, and then let's go in the back with a fluorine. Okay, so we can reposition any two of these and make a stereoisomer out of it. It won't be the same connectivity, right? They're connected to all the same carbon, but they'll be in different relationship to one another. So if I picked these two right here, right, and just leave this one alone, and instead put the bromine down here and the chlorine up here, then you have stereoisomers. And that's required for stereoisomers. You need a stereocenter. And all it takes for a molecule is just one stereocenter. If you have two or more stereocenters, then you get into complications. But for now, we're going to focus on just simple molecules. If they look differently, but they're connected the same way in the same positions, and there's a single bond somewhere, say if we had a bigger molecule, say another carbon out here and something else, then they could rotate around single bonds, and that would give you conformers. And all you'd have to do is just rotate it back around, and it's the same molecule. So conformers are the same molecules. It's just that by rotation, their parts are in different positions. And we're going to look at those also. Because depending on what's out here, the rotation may be hindered by, say, steric effects, and they might prefer to be one direction versus the other. That's coming. And then we're going to get to the discussion of whether or not stereoisomers are mirror images of one another. If they're handed, like if you put a mirror in the front, you do like that, you see over here, well, you're going to see my hand like that, but they're not superimposable. Right? Those are enantiomers. If, on the other hand, they're not mirror images of each other, but they still have the stereocenter, then they're diastereomers. And the implication there is you get obviously difference in reactivity, different pathways in a reaction, and the possibility for separations if you have mixtures. Right? Back in the late 50s and the 60s, there was this drug that was introduced called thalidomide, and it was supposed to help pregnant women with nausea. Yes. Well, what they found out too late for some births was that one of the isomers caused teratogen, developmental problems in the fetus, and the other isomer didn't. But the manufacturer didn't separate the two. They marketed the drug with both isomers together, and that's caused the problem. Okay. I mentioned this already. Conformational isomers, all you have to do is rotate around a single bond. And they have the same connectivity. That's obvious. If they don't have the same connectivity, then of course they're constitutional isomers, and that's a dead end. Okay, so how do we deal with conformers? We've done the, let's see, the different ways of projections. In other words, representing three-dimensional structures in a two-dimensional plane in space. So the first one was just simple line drawing, right? Line drawings. And they could be, usually they were like this. Right? They give you some information. They tell you the connectivity, yes, but they don't give you information about three-dimensional arrangements. Right? So they're not very useful for that. Then we had dash wedge. They do give you information about three-dimensional arrangements, but they're very complex and they're not useful for most discussions, most manipulations that you want to do. Now we come to Newman projections. That's capitalized for a reason, because it's named after the inventor. So what we do in a Newman projection is you find the bond around which you want your molecule to rotate. And then you take that bond and you rotate it out of the plane and you look down the bond. Okay. Then you put a circle. Okay. And the part of the molecule that is in the part closest to you is coming out of the center of the circle. Like that. the part that's on the other side that's blocked by some of the components of the molecule comes out of the back like that. So these are in the back, these are in the front. That's a Newman projection. And what that allows you to do is to look at what happens as you rotate. How do these components, these atoms or groups, possibly interfere with one another? Okay. Let's see. That's how you establish the you change the dash wedge into a Newman. Okay. There are several possibilities for the arrangements. If we have, let's see, this arrangement right here would be the second one from the left. Well, there are several of them that are possible depending on what size the groups are. Anyway, these, well, they have names and the names are not given. Okay, that's coming on the next page then. This slide focuses on the angle. So if they're arranged like this, then the angle between this one and this one is 60 degrees. Okay. And that's where I focus my attention. Either that way, or if they're like this, let's see, like that, and then you have in the back, you have this one, excuse me, rid of that, this one, and then it would be that way and that way. Then the angle would be, it's considered zero. We write it like that because they're supposed to be overlap, but if you do that, you can't see the one in the back. So this is really a line of sight for the front and the back. That's 0 degrees. Now, if you focus your attention on the different attached atoms or groups, then we can introduce more degrees. If you keep going around here like this until it's overlapped, then you've got 120 degrees. If you keep going around until now they're opposite one another again, then that's 180 degrees. Okay, we've got names for those. That's coming in a minute. Okay, here we have a Newman projection of a molecule. Now, what would this molecule be? Right? We've got a carbon in the front, a carbon in the back, right? Carbon in the front, carbon in the back. And then in the front, we have a methyl group. I'm going to draw these as simple line drawing first. This one in the front, and then we have a hydrogen and a hydrogen. Just the connectivity to begin with. Okay? This is in the front, and in the back, you've got nothing but hydrogens. Okay? So that would be propane, wouldn't it? Yeah, that would be propane. So what's the question? Draw the Lewis structure of the molecule with the following Newman projection. Well, we sort of did. I didn't put these out the way it was, but that's it. That would be a Lewis structure. There are no lone pairs, right? No free radicals. I think the idea there was to just see if you could get the relationship between the two. Okay. That was simple enough. All right. So if the angle is 0 degrees, we call that eclipsed. And these are all conformers, right? So if we say that, we have different conformations. This is eclipsed for obvious reasons. Right? This is staggered. All right. And there's one other one. We haven't got to it yet. I think the other one depends on the attached groups. All right. So I'm not going to introduce that one until we get there. Now, what does this have to say about the energy involved? If these, and I would look at it in terms of the electrons contained in the bonds. How do they interact with one another? Right? These electrons in the bonds are repelling one another, right? So the farther you can get them away from each other, the better, right? Back to VSEPR. So this would have a lower energy because they're farther away from each other than these guys. These guys are closer together because they're eclipsed and they only have the distance between the bond distances, the major factor in separating those electrons. But this one, you have just not on bond distance, but it's off at an angle. So they're farther away. They should be at lower energy. These should be at higher energy, which means they're not as stable under most circumstances. If all the groups are the same, in this case, say if they're all hydrogens, then that factor gives you a sine curve. Okay. All right, that's nothing new. We've been there already. I introduced the concept of electron repulsion. Right, so we've covered that already. Let's look at the idea of torsional strain. What is torsion? You might remember automobiles and trucks and vehicles that used, rather than springs, they used torsion bars. You have one end locked in place, and the other end, let's see, it would be like this, be like that, and then the wheel would go up and down, and it would be locked on the other side end of that torsion bar. And as we tried to twist the bar, it would resist it, just like a spring, right? So that's what we mean by torsion. It's a resistance to twisting. So the torsional strain would be higher in the eclipsed because they're getting in each other's way, essentially. And if the groups, rather than hydrogens, if the groups are very large, then the torsional strain would increase. Like if we had a methyl group here and a methyl group here, then we'd have those hydrogens sticking out on either side, and they'd be closer together, and that would add to that would be an increase in the energy that we'd have to store in that twist in order to maintain this conformation. Okay. So these are rotational energy barriers. They're, when we say energy barrier, you have to put that much energy in to get it to that position, right? It resists that particular conformation because it requires an input of energy. In this case, we've determined experimentally that there still are a small number of molecules in this. This would be ethane. In this ethane molecule would be in the eclipsed conformation. Excuse me. 2% molecules. No. I'm misreading that. Sorry. Okay. Get used to it. I'll try to confuse you several times. That's only because I get confused with my own slides. Okay. All right. So what is that other graph trying to tell us? Percentage of molecules with a certain amount of energy. Oh, I see. The difference between the staggered low energy and the eclipsed high energy is about 12 kilojoules per mole. Okay, so that's the amount of energy that has to be input in order to get this rotation to go to that position. And there are only about 2% of the molecules that have that amount of energy. So most of them are going to be in this position. And if we can do a one-to-one correlation between percent and confirmation, I would think that most of them, 98%, are going to be in this confirmation. Now, when they're doing this rotation, if there's enough energy, say, where do they get their energy? They get their energy from temperature. And that means collisions. When they collide with one another, they transfer energy. And if one of them has this extra energy and it collides with one of these, it could throw this one into an eclipse form confirmation, and this one would go back to the staggered. So that's how I look at it. It's an averaging effect. It's a statistical approach. Okay, so here's another one. In this case, we have a bromine on the number 1 carbon. All right, we can use this one. We have bromine here. And let's see. It's probably more stable if we put it up there and look down the barrel. Then we see the bromine down here and a bromine up here. Because bromines are more electronegative and bigger than hydrogens, they're going to accumulate some electric charge. Like this bond is going to be polar that way. So you're going to accumulate some negative charge here, some negative there, and then the positive spread throughout the rest. And what that does is, based on size and charge, slight charge, they're going to prefer to put the bromine one here and one here, as far away from each other as possible. And that's why this curve is not as pretty as the previous one. The lowest energy is going to be the staggered. And there's the other one. Okay, the eclipsed is going to be the highest energy. If you put a bromine up here and a bromine up here, then they're going to repel each other. And they're going to sterically interfere with one another. So the lowest energy is this one. The highest energy would put the bromine here and the bromine here. Well, what if you put the bromine, let's draw another one. Let's see. If I put like that, and then I did this. If I put the bromines, rather than being eclipsed, they're just slightly offset by about 60 degrees, right? 60 degrees. That relieves some of the strain. So in that case, this is called the gauche conformation. And it gives you some relief in the amount of energy required. It's kind of it's a partial dip in the energy required. And then if you try to eclipse a hydrogen and a bromine in those two lower humps, then you still have an eclipsed conformation, but it's not. Seems like they would have a, let's see, eclipsed, staggered. They're saying, okay, we're adding another term also. These bromines are said to be anti to each other. Okay. So the anti-conformation is where the bulky groups, in this case, we're saying bromine is bulky, which it is. It's pretty big compared to hydrogen. Are 180 degrees apart. Gauche conformation puts them 60 degrees apart. So here, this is gauche. And anti puts them 180 degrees. Well, I already said that one. Okay. So we're trying to rationalize why a certain amount of energy is required to get to a different conformation. And the idea here is, where does the molecule spend most of its time? Which conformation? And that varies depending on the attached groups. Okay. Okay, I call this a line drawing. They're calling it zigzag, which is all right. I guess technically a line drawing would just be a straight line. Like if I drew this one out like that, right, and then put a bromine here and a bromine here. Maybe a hydrogen here, like that. Hydrogen here, hydrogen here. That would be a line drawing. Zigzag conformation. So what we're trying to do here is explain why the zigzag is the most stable form for an alkane. If we zigzag them, that puts the bulky groups as far away from each other as possible. Every time you go from one carbon to the next, they're anti to the one before them. And that's the lowest energy. They can still rotate around those bonds, but they spend more time in this conformation than they do in the others. Okay. All right, now we're going to get really complicated. As if this wasn't bad enough. What do we do when we have rings? 5 and 6 membered rings. And these are examples, right? Menthol has a 6-member that has a hexane ring in it. The steroids have 4 fused rings in them, 3 6-membered and 1 5-membered. So we want to look at what effect does a ring structure have on the conformations. So if we look just simply at strain, ring strain, we find that the ring strain, in other words, and we're using, of course, cyclohexane has the least strain because it gives us, let's see, if you look at individual carbons and say you have these 2 hydrogens, let's say this one is comes out. We're in the plane here. So these hydrogens are like that. There's your carbon. These bond angles are 109.5 degrees. Just what we would expect in a tetrahedral arrangement. Right? No strain whatsoever. They get the farthest apart from each other as possible with no strain whatsoever. So that's where we're starting with cyclohexane. Now, if you try to open the bond between carbons, right, open the bond more, then you add strain. So cycloheptane would be like that. But if you remove one of the carbons and you try to make a 5-membered ring out of it, then you're reducing the bond angles. And that adds more strain. So if we go from cyclopentane and cycloheptane, the change in conformation, the movement around that any one of these carbons is about the same as far as ring strain goes. Now, when you get, and this is not a big deal, right? We have lots of 5-membered rings. in organic compounds, in biochemical compounds. Table sugar, for instance, right? It's a disaccharide. It's glucose and fructose. They're both 6 carbons, but the fructose is a 5-carbon ring, right? And it works just fine, right? Even to the point of polluting our food with high fructose corn sweeteners. Anyway, once you move from 5 to 4, then the string is massive. And the bond angles now have decreased even further to 90 degrees from 109.5. You're adding massive strain in that ring structure. And it's even worse for cyclopropane. Right? That's only, what, 60 degrees, right? No, yeah, 180 through, so that's 60. So we went from 90 to 60, and the strain is massive. We can look at it in terms of torsional strain, how it tends to bend, or steric strain, how as we get closer here, these start to interfere with each other. Right? If we decrease that angle, then these groups interfere with one another sterically. I've already mentioned angle strain. These are all, okay, this goes back to my motto. Right, nature just does what it does. We try to explain it. Right, all those different terms are focused on one concept: strain and stability as a consequence. Right, 3-ring groups independently or on a molecule will be more reactive because they want to release that strain. Okay, rank the following compounds in order from least ring strain to greatest. All right, that should be fairly simple. But they stuck a nitrogen in there. All right, let's see. Okay, there's only one nitrogen for each molecule, so they're relatively fixed in the way they behave. All right, yeah.
Is it B, A?
Least strain would be B, then A, then D, and then C. Should be, yep. Let's see. BADC. Yep, there it is. I like simple problems like that. Okay. Now, before I drew the cyclohexane as a flat ring structure and simply focused on one carbon, and then I put the hydrogens either out of or into the board. But the fact of the matter is, any one of those carbons, we could take 3 of those carbons and put the bonds to those carbons in plane. But the other 3 would have to have all 4 bonds out of plane because of the way that we have to have the 109.5 degree tetrahedral angle. Right. So now we've got to devise a way to represent these 6-membered rings so that in 2 dimensions. And the first one, well, we're going to get there. Now, essentially no angle strain. Actually, it's 111 degrees instead of 109.5. Let's see, why would that be? I don't know, not yet. I'll figure it out. As soon as I do, I'll tell you. Unless you figure it first. Got any ideas why it would be greater than 109.5?
You're talking about
The bond,
where it says 100.
yeah, the bond angles. Yeah. Is it maybe a steric effect? Right? Because parts of that ring, right, those things are all up here, whereas with methane, it was just hydrogens out there. Right? But we've got these big parts of the molecule in the ring that are trying to push away from each other. That sounds good to me. I'll go with it. Now, we're going to learn how to draw this chair conformation. But before we do, that's one way of drawing this molecule so that we get that angle in the bonds, the 111-degree angle in the bonds. We see right in here between these three, that angle will be 111 degrees. And it's going to be the same for each one. And the chair conformation is one way to write it. In fact, that's one way that it's a conformation of the cyclohexane. You can get that one. You can also get a boat to where both of the ends are pointing up. And it will flip back and forth between the chair and the boat. But if we're just looking at the chair and we turn it around so that we look down, but say my eye is on this side over here, then what we see is two Newman projections side by side. Because if we're looking down this way, these two bonds they can rotate some. They're not as free to rotate as others, but since it's a ring structure. But if we turn that on its side, then we get that Newman projection with it's like a double barrel shotgun. And this will inform us if we add groups or atoms attached to that ring structure, then the Newman projection will help us decide which one is favored, which one of the conformations for cyclohexane is favored. Okay. I left this one out. You can also have an envelope conformation where you have one end sticking up and then the other end is straight out. That, to me, I think would probably be kind of mid-range energy input to get there. I'm sorry, we're cyclopentane. I gotta read my own slides. So cyclopentane is stuck with the envelope conformation, because if we try to put it flat like that, then that's increased energy. But if it flips over like that, now we got another envelope. Okay. And if we're looking down a bond, the 5-membered rings, we can only get one Newman projection out of that one. I mean, we can rotate the molecule around and get another Newman down a different axis. Cyclobutane, I think what we're trying to do here is show the effect, using the Newman projection, the effect of strain on these molecules and how it presents itself in a Newman projection. The cyclobutane is going to be puckered. Well, there we go. Cyclopropane, it has no choice but to be eclipsed. Right. So that's another explanation for why the bond strain is so high, and the energy required to maintain that conformation is so high. And if you have a high energy already in the molecule like that, then it only takes a little bit more energy to break those bonds. That's why they're so reactive. Okay. So how do we arrive at these ring strain values? Well, one of those is heats of combustion. if we take the compound and we combust it with oxygen, obviously, we're supposed to get carbon dioxide and water and some heat, right? That's the delta H, the enthalpy of combustion. So what we're trying to do is prorate the heat of combustion for individual carbons, CH2 units. Right? Why? Because in a cyclohexane, for instance, how many hydrogens for each carbon? There's two, right? So this would be a CH2 unit. We could do the total combustion for this molecule divided by 6, and that would give us a heat of combustion per CH2 unit. That's what we're after. So we say, how many of those units do we have in the molecule? Divide that into the enthalpy for the whole reaction. Okay, when we do that, we find that the heat of combustion for cyclohexane is 3,690. And the heat of combustion for cyclopentane is lower. And the reason for that is we're building in bond strain. In other words, it's already part of the way there. So we're not going to get as much energy out of it because it's already built in. So if we divide the total by 6 or the total by 5, we find that that type of calculation gives us a higher energy per bond. And if we use the reference here as 0 for the cyclohexane, then we just subtract that amount from the cyclopentane, and we find that the difference there is 5.4 kilojoules per mole in excess strain on the bond. Okay, and that's multiplied by how many carbons you have. That 27 is what we saw in that slide where we compared each one. Okay, that's how they got that number. We can do that for all the others. We just don't have a slide for it. Okay. All right. I thought we were going to get into drawing the cyclohexane. Maybe we better do that. I'll tell you what. Let's put a model together first. Cyclohexane. So be sure you have the tetrahedral carbons. Slide some trigonal planars in there, so you don't want any of those. And that's tetra, that's tetra. Okay, that's good. And you want the straight. You want these straight guys right here. You get these long ones are for double bonds, triple bonds. So I put your 6 carbons together first. 1, 2, 3, 4, and 2 more. Okay, that's tetrahedral, good. And it really doesn't matter which hole you put it in to start with, because once you match them up, you won't have any choice. And we're not going to put, well, I guess we could put hydrogens in there, but that would kind of, well, maybe that would emphasize, yeah, I'll put hydrogens in there too. Uh-oh, I got a trigger on here. That one snuck in on me. And it's trigonal tetrahedral. There we go. We got any more spooks in here? Yep, there's another one. Well, they need to be in different color. This is, nope. There we go. Okay. We're getting there. And this one goes right here. Okay. Yeah, how did that one get there? Send it to the boneyard. There we go. It's hard on your hands if you have arthritis. Two, and two for this. There you go. One more. Why is that one on both sides? Oh, I know why. I got a hydrogen with holes on both sides for ethers. But it'll work for this one. Okay. So if they're coming along.
They're already put together.
Yeah. I'll tell you what. You guys continue with that and I'll go see if our printer's done. Halfway there. Go at the staple. See, where's the staple? Here it is. And then the staple's in it. At least it's cold over there. Should have punched holes when I had the opportunity. Okay, how we coming? Done, and done. All right. Okay, it would be easier to see if we had bigger models. But the chair conformation is going to point this one down and this one up like that. Okay. So if you can imagine a plane this way through the molecule, then we identify the attached hydrogens or whatever else is there as axial if they're pointing up or down, and equatorial if they're roughly in the plane, right? That one's a little above, but it's considered equatorial, 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 and this one is equatorial. So it should have 6 equatorial hydrogens and 6 axials. Right, so I have 3 on top here and 3 on the bottom. Those are the axials. All right. So if we try to draw these in a three-dimensional, if we try to draw the 3 dimensions in a 2-dimensional plane, the best way to do that is to first start off with 2 parallel lines, only they're slightly offset. So I would draw one maybe like this, and then offset this one about that much. Right? Okay. Then pick a point. Let's see. If this one has made room on this side, so I put one up here about, let's see, let's put one up here. Let's try to make it a little more room. And then one down here like this. Okay. Then connect. So connect this one, that one, this one, that one. So what you'll notice is if you get it drawn right, is these 2 are parallel, these 2 are parallel, these 2 are parallel. That's not a very good drawing, but such as it is. And this is the chair conformation. Now, what can happen is this can flip up and this can flip down, and the chair, we change the conformation, but it's still a chair by flipping those around. Actually, the bonds that rotate are these 2 right here to get it in that position. And if we take our model and let's say this one's going to be down, so I'm going to go this side. This is down, this is up. And if I try to flip this one this way, this one this way, then we have flipped our down, this one up. This one should be, now this one's down and this one's up. So what I haven't done yet is to draw in the axial and equatorials. So if you start from anywhere and just number your carbons, that, then if this one's axial, then this one's going to be axial in the opposite direction. If this one's axial, and in order to represent an axial for this one, we have to sort of draw it at an angle like that. This one's going to be up, down, up, down, up. So this one would be, this one should be up also. This one should be up like that. Then the equatorial is going to be this way, And this one is equatorial, and this one is equatorial. So it's going to be like that. It's opposite this one. And this one's going to be equatorial. That one's down. So this one has to be equatorial that way, and equatorial this way. So we should have 1, 2, 3, 4, 5, 6 axial, and 1, 2. This is kind of going back into the board. 1, 2. Actually, this one should be out like that. That's better. 1, 2, 3, 4, 5, and 6. This one should be out like this. Sorry. Think of them as mirror images of each other. Now, I've got links in Brightspace to what is she called? Leah Forsyth. If you've seen that one before, if you've seen it in the Brightspace, she's got some good videos, particularly on drawing these things. And so it might help to take a quick look at one of those. Okay. So this is known as a chair flip. Right? Rotating around these two bonds, we take this one down and this one has to flip up in order to maintain the same energy level. And that's for cyclohexane only. We haven't attached any different groups to it yet. So those should be at the same energy level. They just flip back and forth. And they do that like a quadrillion times a second. All right, on an energy diagram, like I said, the chair one direction is at the same energy level as the chair the other direction. And the boat puts those hydrogens, if we flip the boat up, all right, let's see which side's down, which side's up. Down, up. If we say flip this one down also, now we have a boat conformation. Both ends are flipped up. That introduces a significant steric hindrance. These hydrogens are getting too close to one another. So we increase the amount of energy required there. But if we torsion it just a little bit like that, it's in between, it's a twisted boat, then we reduce the amount of strain. If we put the chair conformation, if we bend this one down and leave this one up, then what we're doing is we're minimizing the steric hindrance, steric effects, but the strain is still there. And the strain is excessive. So the half chair is the highest strain on cyclohexane. Okay. Okay, they're calling it the flagpole interaction. So if you have the boat like that, then you have flagpole interference. And let's see what they do. They turned it around, strain in the boat conformation. Okay, what we're doing is when we do that, we're drawing these hydrogens into eclipsed conformations, particularly, let's see, these two right here. So I've just rotated around like that, well, like that. And now we have Newman projections down these two bonds, and we're eclipsing these hydrogens with each other. Okay. And we already know that the eclipsed conformation is the highest energy. Okay. Well, there we go. Let's see. Did I draw that one? Okay, that one's turned around the other direction. This is up and over. The hardest part for me is recognizing with this type of line drawing, recognizing which one is axial and which one's equatorial. It takes a lot of practice in drawing it correctly, actually. Okay. Oh, all right. Now we're going to get in. They finally get into drawing them for us. All right. Carbon-carbon bonds toward the bottom of the ring are interpreted as being in front of the plane of the paper. Okay, so it's showing us those three bonds in front. This one, and this one are in front of the paper. So you're looking at it kind of like this. And these would be behind the paper. These three here would be behind. Axial bonds are vertical and alternate up and down around the ring. Okay, so alternate up, up, down, and this one should be, that's down, and this one's up. This one should be up more. And this one should be down more. Yeah. And then equatorial bonds alternate slightly up and down around the ring. So this one in the back, okay, that's good. And this one kind of points off at an angle like that. And this one points up at an angle a little bit. There, there. This one should point down just a little bit. And this one should point down like that. That's on the wrong side, isn't it? No? Yeah. Well, it takes practice. All right. Yeah, you see parallel bonds. What? These bonds are parallel, these are parallel, these are parallel, but the axials are parallel to one another, and the equatorials should be parallel to one another also on opposite sides of the ring. Okay, this is their idea of instruction on how to draw the things. I think Leah's video is much better. So let's not spend time on it here. Let's look at, I need to look at Leah again. Okay, what happens when we monosubstitute the cyclohexane? Well, which would be the preferred conformation? If we attached a methyl group to one of these, and it doesn't matter which, because they're all equal, these carbons are all equivalent, so we can put it anywhere we want. So if we put a methyl group out here on the end, like that, would it be better there or here? Right? It's either or. That's or, not either. It's or. Which one would be the lowest energy? The one that had the least steric interference, right? So it would be better off as an axial substituent, right? So if we did a chair flip, say we did a chair flip from this one, like that, where would that put the chair flip would put this into an equatorial position. Now, would that be actually, what other things are around it? I see you put one in there. Which one would be more interference? Probably this one. And if we put equatorial sticking out there in open space away from everybody, you can see from this one, so get my arrow here, that we're getting close to these other hydrogens. Over here, we're moving further away from them. Yeah, what they said. Equatorial is more stable because of steric hindrance predominantly. So if we looked at that in terms of the Newman projection, right, we rotate it around and we look, actually, we're going to rotate it around and put the methyl group in front. So we want to look down the bond between 2 and 3. And that puts, and if the methyl group is axial, it's gauche to the hydrogen, and the methyl group, the hydrogens in the back. The red one is gauche to the hydrogens in the back. That's less stable. If we move it into the axial position, then it's anti to the nearest hydrogens, and that is more stable. All right. So this steric hindrance from chair flipping, it also depends on what group is attached. What is the substituent? The percent conformation for each, if they're both hot, if all of them are hydrogens, you get an equal distribution of one chair version to the other chair version. If we introduce hydroxyl, then we're going to get more of the axials, 81%. And that's not so much steric hindrance as it is electron repulsion, because oxygen is more electronegative, tends to accumulate electron density towards itself, and it wants to get way away from the other guys. Nitrogen, which is also capable of hydrogen bonding, so it's not quite as electronegative oxygen, but it has those two hydrogens out there. So we're introducing steric hindrance as well. And that pushes the equatorial conformation to a higher level. And then the methyl group, of course, because of its bulk. And if we put an ethyl group out there, it's even bulkier. If we put what's a CH3 taken twice? That's a propyl group, right? 3 carbons. So that isopropyl group is even bulkier, and it pushes it to a high level. What's CH3 taken 3 times? That's a butyl group. The butyl group is massive, right? So it's essentially everything is in the axial position. Very little, just almost immeasurable in the, equatorial. The axial is almost immeasurable. Okay. So we haven't talked about Haworth projections yet, have we? No. Well, why is that there? Well, maybe it's sort of it's a tease. Maybe try to get you to wondering, all right, what is a Haworth projection? It's kind of like a, let's see, we've done the chair. And then next, I think we're going to go to Haworth. Haworth is a simplified version of the chair. And what it does is it flattens this thing out into a six-membered ring. Of course, you can use it on any membered rings, but it flattens it out so that we don't have the problems with trying to draw it this way. So all right, we're borrowing terminology from double bond substituents, cis versus trans. So when you're looking at a chair conformation, cis would be on the same side of the bond and trans would be on the opposite side. That still holds. Okay. We're also introducing this concept so that when we get a chair flip, the substituents remain in the same relationship to one another. If they're cis in one chair, then when we flip it, they're cis in the other chair. Now, they may go from axial to equatorial, but if they do that, then their neighbors go opposite so that we can maintain the cis or trans conformation. And I think that's one of the advantages of the Haworth projection, is it allows us to do this cis-trans relationship easier. So here's what the Haworth projection, and now we're dipping our toes into the water. Here we had only one change in substituent. If we put another methyl group on there, then the other methyl can either go here or here. Right? So if it's here, it's trans, right? It's axial this way, axial that way. If it's here, then it's cis. Okay. If we draw the cyclohexane ring so that the two groups are coming out toward us, then they're both out of the plane, they're cis. Relative to the bond, they're on the same side of the bond. If we have one going into the plane, one coming out of the plane, then they're trans. And in order to represent those in a Haworth projection, we simply take that dash wedge representation of the cyclohexane and rotate it so that it's not quite, but almost 90-degree rotation. And then we get, if those X and Y are coming out of the board, then they go up as we rotate. Right, we rotate this way, they go up. If we rotate the other one, then the one that's down goes into the board. Now we got one up and one out of the board. But the Haworth projection simply keeps them in their cis or trans relationship. Okay. And this Haworth projection, typically we draw just straight lines from this part of the molecule, and then this one are a little fatter. And then this one is big fat. Trying to represent the fact that this part of the molecule is coming out of the board. Okay. And I think to simplify, we don't put dashes back here to show us. If we rotate around this axis, then these are actually into the board. That's a Haworth projection. Yeah, there we go. So all these different projections are designed to be used to answer different questions. Which one's easiest? Which one gives us the most information for the least effort? Okay. So, our example here, if we were to say cis 1,3-dimethyl cyclohexane, then the methyl groups would be on the 1 and 3 carbons. And if they're cis to one another in a Haworth projection, they're going to be well, in this case, we're making them vertical. I think it's easier to see it that way. So what would that look like in terms of the chair conformation? Well, the chair conformation means that if they're cis to one another, they're either they're both equatorial or they're both axial. Right? And the chair flip would do that. The chair flip would if we draw them equatorial, then the chair flip would make them both axial. So they maintain their cis conformation. If in the bottom one we make them trans, then when we write them in the chair conformation, one of them is equatorial and one of them is axial. Chair flip would change the equatorial to axial and the axial to equatorial. That's the relationship between the two projections. Okay. You got your methyl groups on there? Is it making sense with it? Okay. All right. So we've got the constitutional isomerism changes connectivity. So cyclobutane would have different connectivity to but1ene. It's still got 4 carbons, but you have a ring structure for one and a zigzag for the other. Now, since if you have single bonds, remember, you can rotate around those bonds, and when you draw them, they can look different, but they're not different. That's what we're trying to show in this bottom two. If we look at the zigzag with those 2 methyl groups on the 2 and the 4 carbons, then if we let's see, which bond would we rotate? If we flipped and then rotate, yeah. So if we take the left one and flip it, that puts the number 2 methyl group up. It also puts the number 4 methyl group up. But then if we rotate around the 3,4 carbon, then that changes the position. That puts the methyl group in the zigzag position, and it puts the ethyl as an apparent substituent. But they're the same molecule. So I think the way around that is to name the compound. Right? If you can give both of them the same name, then you know that you don't have a conformational isomer. Okay. Identify the parent chain. Number the carbons. Establish the relative connectivities along the parent chain. All right. Okay. So they're essentially saying what I just said. If you go through this procedure and name the compounds, come out with the same name, then you don't have constitutional isomers or structural isomers. Okay. And that's what we're trying to show here. All right, here's a concept that's very, very useful. It's called index of hydrogen deficiency. And this is used when we have double and triple bonds involved. When we say a saturated molecule, there are only single bonds. between the carbons and no rings. Right? If we unsaturate any one of the bonds, then we either produce a ring or a pi bond. And the index of hydrogen deficiency. I left out a word. Index of hydrogen deficiency. I left out the D. Of a given molecule is that half the number of hydrogen atoms are missing from the molecular formula of any of these comparative saturated molecules. So here's the way I look at it. Say we have pentane. All right, so we're going to have hydrogens here, here, there. Actually, there are three here. Here. These are hydrogens. So this is a saturated molecule, only single bonds between the carbons. So what would happen if we formed a double bond in here somewhere? And carbons only have 4 bonds, right? If I put a double bond right here, what do I have to do? I've got to get rid of a hydrogen on that side and a hydrogen on this side. Now we have 1, 2, 3, 4. 1, 2, 3, 4. So how many hydrogens did I lose? I lost 2 hydrogens for each double bond. It's deficient by 2 hydrogens. Okay. The hydrogen deficiency, though, is the number of hydrogens lost divided by 2. Because we lost only 1 from each carbon. So each double bond contributes a unit of 1 to the index of hydrogen deficiency. Triple bond contributes 2, and each ring contributes 1. If we were to take this 1, 2, 3, 4, if we take that 5 and put it into a ring structure, right? Just take these two and hook them together. Then we didn't form any pi bonds, but if we do this, those are all hydrogens. 2, 4, 6, 8, 10 hydrogens here. How many did we start off with? Well, if we didn't use up our hydrogens, then we would have 2, 4, 6, and 6 is 12. So 12 hydrogens is saturated. 10 hydrogens means that it's the index has been reduced by 1 just by forming the ring. So if we calculate the index of hydrogen deficiency for this molecule, we look for pi bonds. We have 1, 2, 3, 4 pi bonds. That ring on the left is what? Benzene. It's a benzene ring. So we have 1, 2, 3, 4 pi bonds. 4 pi bonds. And we have 1 ring. 1 ring. And what else? That's it. So that's right. Count the number of pi bonds and the number of rings, and that's your index of hydrogen deficiency. So how many hydrogens were involved? 10. Okay, how about the next one? Well, we've got a triple bond there in that, what is that group called? Oh, mine's gone blank. I'll come back to it. Nitrile. That C triple bond N is a nitrile group. It's a nitrile substituent. So we've got 2 pi's there, got 2 pi's on the other side, and 1. So we have 2, 4, 5 That's it. It's got the same index of hydrogen deficiency. This is kind of like, let's see, where we learned the rules for determining an atom's oxidation state. Right? We went to all that trouble to learn all the rules, and you're probably wondering, what good is it, right? So maybe on the next couple of slides, we'll find out what to do with this information. The other one has 2 pi bonds and 3 rings. So that's each one of these has the same index of hydrogen deficiency. Okay, now we're going to try to explain what that means. Actually, where we're going with this is, if you know what the index of hydrogen deficiency is from a given formula, then you should be able to construct, if you're given the molecular formula, right? It doesn't give you any structural information, but you've determined the molecular formula from bench chemists' activities. And you also have determined the index of hydrogen deficiency. Then you can propose different structures that satisfy that condition. I think that's where we're headed. So, in the A, this ethane molecule has 0 hydrogen deficiency index. Right? There are no double bonds, there are no ring structures. Right? If we form 1 double bond, then we have a IHD of 1. If we form 2 double bonds, making the proper name is ethine, but that's acetylene. Then we have an IHD of 2. In the bottom case, we have ethanol, right? It has the same index of hydrogen deficiency. If we form a ring between the 2 carbons with oxygen as the bridge, then we have 1 ring and the index is 1. All we're doing here is illustrating that you can have the same IHD for different conformations. How about this one? What's the IHD for that one? Naphthalene. 1, 2, 3, 4, 5. We got 5 pi bonds and 2 rings. So we should have an IHD of 7. Now, if you draw the structures with like that to represent reality, then it's harder to assess the IHD. So we need to draw it the old-fashioned way. This naphthalene is an aromatic compound, but if we draw them this way, then we get the ability to calculate IHD. So there you have 7 IHD for naphthalene. Naphthalene. We put that in woolen clothes to keep the moths out. I think that's one way. There's another compound, I'm trying to think of it, that we can also use. Okay. So a saturated hydrocarbon has 2N plus 2 hydrogen atoms. And if we say, for example, if we have C6, right, and it's an aliphatic hydrocarbon, like straight chain hydrocarbon, then we would say 12 plus 2 is 14. I like to say 6 plus 1 times 2 gives you the same value, 14. That is saturated. It would have an IHD of 0. If, on the other hand, we incorporate nitrogen or oxygens or halogens, then the number of hydrogens is decreased. Right? For oxygen, we can form 2 bonds with oxygen Nitrogen we can form 3 bonds, halogen we can only form 1 bond. So how does that impact the IHD? That's what we're going to do on the next slide. Right, if we add oxygen to the atom, that leaves the number of hydrogen atoms unchanged. Right, because we inserted that oxygen in there, and look, we didn't lose any hydrogens. Right, the N group would have been a methyl. If we plug an oxygen in there with its hydrogen, then there's no effect. So if there's oxygen in the group, you can ignore it. And if there's an oxygen in the formula, you can ignore it for calculating the IHD. If there's a nitrogen in there, then we have increased the number of hydrogens by 1. Okay, so the number of nitrogen atoms will add 1 unit to the IHD. Excuse me. No, yeah. Number of nitrogen atoms adds a hydrogen. Okay, let's focus on the number of hydrogen atoms first before we calculate the IHD. Let's do that. So with the aliphatic hydrocarbon having 2N plus 2 hydrogens, then if we have a nitrogen added, right, we have the same number of carbons, but we're going to add a nitrogen. Add an oxygen, no effect. Add a nitrogen, it adds that many extra hydrogens. If we add a halogen, then it substitutes for the hydrogen, and we reduce the hydrogen number by 1. Okay. All right. Now, what? Hold on a second. Okay. All right. So what's the IHD for this one? Well, how many hydrogens do we start with? We started with 8 hydrogens. We've got 2 oxygens, no effect. We've got 1 nitrogen, that bumps it up to 9, but we've got 3 chlorines, that brings it back down to 6. And 6 divided by 2 is 3. If we count the number of hydrogens and divide by 2, then we have the IHD. Okay. Now, we're not saying anything about whether or not this is a cyclic compound. So, in my mind, that could influence the IHD. We have to assume that this is a straight chain. Otherwise, if it had any cycles in it, or if it had any double bonds in it, that would impact the IHD. So we're starting from this position. The IHD of this one, if it's a straight chain, is 3. Okay. So once we determine the IHD, then we can draw all the possible backbones first. Then we can add triple bonds to achieve the total IHD, or we can introduce ring structures. We can add our halogens to reduce the number. So what about this one? The IHD for, what would this one be? Let's see, C4 would be butane, difluorobutane. We can't say where they're positioned because we're not told that. We can't say like 1, 2 or 1, 3. So this is only a partial name. So what would be the IHD for this one? Well, if we count the number of hydrogens in butane, it would be C4H10, right? So we got 10 hydrogens to start with. We've got 2 fluorines. So we're down to 8, right? Hold on a second. Yeah. Oh. Ten would be saturated. This would be saturated with an IHD of 0. That doesn't make any sense. The IHD should be -2, -1, excuse me, -1. So why are we saying that? Okay, here's what I think they're doing. Since we substituted the fluorine for a hydrogen, then we still have 4 bonds to every carbon. That's why they're saying that IHD is equal to 0. But if we go back to their rules, if we go back to their rules and say the number of halogen atoms decreases the hydrogens by 1 each. You know, does that confuse you too? Yeah. The only way it makes sense is if we say that fluorine is replacing the hydrogen. So we're not changing the hydrogen efficiency because there's a bond there to the carbon. All right, I'm going to have a word with Dr. Carty. So if we draw all the possible isomers for this molecule, what could that be? Well, if the IHD is 0, we can't have any pi bonds. We can't have any cycles in your ring structures. So we could either have this one. Oops, too far. 4 carbons with the attachments. Or we can take this carbon and put it up here. Like that. 1, 2, 3, 4. 1, 2, 3, 4. That's the only possibility. Where else could you put it? Right? If we put it over here on this side, you got the same molecule. So those are the only 2 backbones we can have for this formula. Okay, no double, no triple bonds. Then we can add fluorines. Right? So if we have this one, where can the fluorines go? Well, for this, excuse me, let's get rid of that. If we add the fluorines to this one, we could put one on the end. Right? We could put a fluorine here. Or we could put a fluorine here. What if we put a fluorine over here? That'd be the same molecule. But there are 2 of them. Right? So let's get to the second one in just a minute. We're going to add 1 fluorine first. If we did this one, we could put a fluorine here. Right? If we put one over here, it'd be the same molecule. So we could put one off of that carbon, like that. Right? I think that's what F is trying to show us. Oh, wait a minute. No, if we put a fluorine there, then that's the same molecule. That won't work. It has to be here, off of that number 2 carbon. If we put a fluorine on this side, then it's just rotating the molecule around and you get the same structure. I see that now. Okay, that's one of the fluorines. Now, let's put the second fluorine in there. So where could the second fluorine go? Well, on this molecule, we could put the second fluorine here. Yep. Or we could take this fluorine, we could put a fluorine here. That. Okay. What if we put a fluorine on the third? It's possible. Fluorine here and a fluorine here. Or we could put fluorines on the ends. So I'm going to leave that there. Just draw another one. Okay. Those are possibles. If we started with this one, and we put a fluorine here, that's the same as that one. So that's why they X'd it out. If we put another fluorine there, that would be valid. If we put a fluorine on the second carbon, right, we had a fluorine here and a fluorine here, that would work. If we put a fluorine here and on the end, that would be the same as this one. All right. So we don't need that one. Okay. If we come down to this one, that's for all the straight chains. So we got 1, 2, 3, 4, 5, 6 possibilities. 6 possibilities if the chain is straight. If the chain is branched, here, 1, 2, 3, 4. Then if we put one, 1, 2, 3. If we put one here off the number 2, that's possible. Wait a minute, 1, 2, 3. Hold on a second. Let's do it like this. There we go. Then off of that carbon, we can have 2 fluorines. Okay. Or if we keep this one here and this one here, that should be different. And these are different structural isomers, constitutional isomers. By the way, we can position different connectivity. All right. Then if we have this one again and we put fluorines on the end, are those different? Yeah, those are different. But if we put one here, if one's there and we put one up here, that's the same as this one. I mean, the same as this one. So we only get 3 possibilities out of this one. So we got 6 there and 3 here. Those are all the possible structural isomers for this formula. And they all have IHD of 0. And the only reason that the only rationalization that I can bring to that is that we've replaced one hydrogen with one fluorine and it's a wash. Okay, are we even getting close to the end of this chapter?
Yeah, so it's 3, 4, 5, 6.
Okay.
And then 78 for the next chapter.
Okay. Well, we'll take a short break, of course. Okay. How about all constitutional isomers for C3H6O? See, I'm going to erase that. C3H6O. All right. This one has an IHD of 1. Okay, we have 6 hydrogens. How much would be if it were aliphatic? C3H what? H8, right? So we're missing 2 hydrogens divided by 1 is an IHD of 1. That's how I figure that one. Okay. That would be a saturated aliphatic hydrocarbon. Okay, so our structures must either contain a ring or a double bond. So if we go the rings first, we could have a 3-membered carbon ring or a 3-membered heterocyclic, or we could have a 4-membered ring with oxygen involved. Right, that would be the what's the terminology for that? Backbone. That's the backbone. Now, have we accounted for the hydrogens in that case? Right. For A, we need 6 hydrogens. Right. So that apex carbon is going to have an extra hydrogen. So 1, 2, 3, 4, 5, 6. Okay, A's got all its hydrogens. The next one, 2, 3, 4, 5, 6. Yep. 2, 4, 6. Okay, so A, B, and C have all their hydrogens. If we use straight chain, then we can have 1, 2, 3 with a hydroxyl on it. We can have an ether, or we can have a hydroxyl on the number 2 carbon. Those are possibilities. That's with no rings. Now, do we have the right number of hydrogens down there? 3, 4, 5, 6, 7, 8. Okay, so D has too many hydrogens. E, 3, 4, 5, 6, 7, 8. 3, 6. No, wait a minute. 3, 6, 7, 8. Okay, so D, E, and F are saturated. We've got to put in a double bond somewhere. All right, so if we put in a double bond on the 1s and 2 carbons, then we get G. If we move the double bond over to 2 and 3, we get H. If we move the double bond to the oxygen side, then we get an aldehyde, 2 alcohols and an aldehyde. Okay, I see what they're saying. We don't want to change the formal charges. Formal charges need to be equal. Distributed the same way. Let's see, what does J do? Well, J takes the ether and puts a double bond on the 1 and 2. Right? We can't put one between a carbon and an oxygen. Not if we're going to have the other carbon in there. Can't do it. If we take the branched version, we can put a double bond on the branch. Now, why can't we use L? Oh, it's the same thing. Yeah, L is the same thing as K. Oh, redundant. I misread that. It's redundant. Okay. And then if we move the double bond to the oxygen, then we should get, let's see how many hydrogens we got. On the one on the end, we have 2, 3, 4, 5, 6. Okay. Then H, 3, 4, 5, 6. Okay. I, 3, 4, 5, 6. Okay. So G, H, and I are correct with the number of hydrogens. J, we get 1, 2, 3, 4, 5, 6. Okay, good. And then K, I'm starting at the top. That's 3, and there's none on the second carbon. 3, 4, 5, 6. We're good. And then M, 3 and 6, and none on the oxygen. Okay. So that's good. And those are all the possible constitutional isomers with that formula. All right, we want to, okay. I'm going to introduce a little biochemistry here, I guess. These are, everybody know what an amino acid is? Okay, what you need for an amino acid, you got to have carbon here. You got to have an amine group there and a carboxylic acid group here. This is the alpha carbon. And then whatever you attach out here changes the amino acid, right? That can be different. As long as you have this. Right? And when you form the polymer, polymer is a polyamide. Right? You form an amide between the carboxylic acid on the other molecule with the amine group here. Okay, so in this case, we have leucine versus isoleucine. So that R group over here is like this, 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 right? Yep. This carbon would be right there. Let's do it this way. This would be leucine, right, right, right. Isoleucine would, let's see. No, sorry. That would be this carbon there, like that. 1, 2. Oh, that's right. That's attached to the alpha. Okay, there's the alpha. That was right the first time. If on the other hand, we have 1, 2, 3, 4, 1, 2, 1, 2, 3, 4. If we attach instead to the second carbon, like that, that would be isoleucine. There are a couple of amino acids that do that simply by the point of attachment. Monosaccharides are notorious for constitutional isomers. They are massively complicated. So when you take biochemistry, if you take biochemistry, you'll spend a lot of time on that in that chapter, just on the monosaccharides. Ribose. Ribose is a 5-membered ring sugar. Glucose is a 6-membered ring. Let's see. And the the positions of the hydroxyl groups determine whether it's one. We're talking about these sugars. The position of the hydroxyls determine which sugar it is. And each of these sugars is a constitutional isomer of the other one. Now, if your sugar has these hydroxyls on the carbon chain, and the end unit, the end carbon, is an aldehyde, then this is called an aldose. The sugar, any of those sugars that have an aldehyde on the end are aldoses. If we just move that carbonyl group over one, it makes a ketone, and those are ketoses. The effect that has is on the type of ring structure that can be formed. If you have the aldose with the carbonyl on the end, then the end carbon is the one that goes around and attaches to the hydroxyl on the other end. If you have a ketose, then it's that carbon, the second carbon, that attaches and usually reduces the ring number by one carbon. Okay, so glucose and fructose are constitutional isomers. They have the exact same molecular formula, C6H12O6. It's just, where is that carbonyl group? In fructose, it's on the number 2 carbon, which gives you the 5-membered ring, and the glucose is on the number 1 carbon, it gives you 6-membered ring. But everything else is the same. Okay. Let's see, fats and oils. We talked about saturation versus unsaturation. Whenever you have a fatty acid, you have a long aliphatic chain attached to a carbonyl group. I mean, a carboxylic acid group. And then you have however long that happens to be. That gives you your fatty acid. Now, if the fatty acid is unsaturated, then somewhere in here, you've got one or more double bonds. Okay. And for all naturally occurring unsaturated fatty acids, the double bonds are cis. If a fatty acid has been modified, industrially modified, it's going to be trans. There's no other way. They always come out trans. And those are not healthy. They call them trans fats. So what that does is it kinks the molecule to get the cis conformation. You have this kink in the molecule. And what that essentially does is, for physical properties, it reduces the melting point. So they melt at a lower temperature. And if you're going to fry foods, you want something that will melt at a higher temperature. It generally gives it a higher smoke point, so you can heat it, you can get it hotter if the fats are trans. All right. Oh, good. That's it. We'll move on to chapter 5 after a break. Isomerism part 2. Before I had this wrong, I had 3 and 4. It was 4 and 5.
Yeah, we said that earlier.
Okay. So now we're gonna move on this flow chart from constitutional isomers and conformers to those isomers that have exactly the same connectivity, but the positions in that connectivity are different. And those could be possibly either enantiomers or diastereomers. Enantiomers are these, and they're called configurational isomers. In other words, they're the same connectivity, but they're connected, instead of this way, they're connected that way. They just, all you have to do is change two of them. If they happen to be mirror images of each other, these molecules, then they're enantiomers. If they're not mirror images of each other, then they're diastereomers. The trick is going to be trying to figure out which is which. So they're probably going to talk about it in a minute, but I think the slides might. Alan, if you don't say something first. Oh, okay. I see where they're going. All right. We're going to take this example, and this may be one that I used before, right? It had methane, and we substituted bromine, fluorine, and chlorine for the hydrogens. Okay, you could draw it in the one on the left, you could draw it with the fluorine in front. Well, let's see. Which ones are they changing? Fluorine is forward. Oh, I see. Okay. So with this dash wedge projection, chlorine and hydrogen are in the same plane. Fluorine is forward and bromine is back, but they're on opposite sides of the molecule. So if we put a mirror against one of them, do we get the mirror image of the other one? And in this case, we do. You can see that if we take the one on the far left and then look in the mirror on the far right, then we see the bromine over here in the back is now mirrored bromine in the back on the other side. But if we try to superimpose them, simply just take them and move them like this, they don't match up. They're non-superimposable mirror images. And you can't even flip them around and rotate. So what would you do if you could take the one on the right and flip it over? Right? That bromine, just look at the bromine. Bromine's in the back, right? If you flip it around until chlorine's on the other side and bromine's on this side, and fluorine then becomes in the back. It's dashed, and bromine is a wedge. So you can't superimpose them by rotating the molecule either. Okay. And that's what this slide is trying to do. Right? If you hold a hydrogen up here, okay, and just rotate around that bond, then what do you get? Well, you get a mirror image, but they're not superimposable. Okay. All the constituents of the molecule in the image are reflected. They're reflected of each other. In other words, they're on opposite sides of the central atom. And every atom is the same distance away from the mirror on either side. So if we go back and we look at the chlorine, this chlorine is the farthest away on the left. On the right, it's the farthest away on the right. And this hydrogen is close to the mirror on the left. It's close to the mirror on the right. That's what they're trying to say with that one rule. Okay. So how do we draw a mirror image? Draw the mirror image. If we're actually taking a structure and trying to draw the enantiomer, how would you do that? Well, you set up the mirror and you put the atoms same distance on the right as on the left. So the carbon is going to be our central atom, right? We put it a certain distance away from the mirror. Then the chlorine, right, is close to the mirror in this representation. It's close on the other side. It's also in the plane. Right, so then we go to the next one. The fluorine is far away on the left and pointing forward. On the right, it's far away on the right and pointing forward. And then bromine is far away and pointing back on the left and far away and pointing back on the right. So that gives you your mirror image. Okay, so here's another term, chiral. Chiral comes from the Greek word for hand, right? So the reason we do that is because this hand is a mirror image of that hand, but it's not superimposable. If I did this, that's not fair because now the back of my hand points this way and the palm of the hand points this way. So this is mirror image, but not superimposable. It's chiral. So we want to apply that to a molecule. So in order to do that, we need to decide, is the molecule chiral or achiral? And remember, A is a prefix, means not, right? Like atom, not cut. Okay, so this molecule, trans 1,2-dichlorocyclopropane. Cyclopropane, and notice that the chlorines are on opposite sides of that bond. So they're trans. Okay, so is this chiral? Is this molecule chiral? So how do you draw the mirror image? Draw the mirror image. Here we go. All right, there's the mirror image on the right. We start by forming, okay, the chlorines are close to the mirror and back on this side, and then up here, they're further away and forward. Right. Now, can we superimpose those molecules? If we rotate them around so that the chlorines are on the same sides of the molecule, now the chlorine on top goes to the back, and the chlorine on the bottom goes to the front. We can't superimpose them anymore. That's what we're trying to show down here. So this molecule is chiral. Non-superimposable. Now that references the entire molecule as chiral. It looks like our hands, non-superimposable. Mirror images. The other way to look at it is if we can draw a plane of symmetry. This is another test for checking for chirality. If we can bisect the molecule in such a way that one half of the molecule is the mirror image of the others, then we have a plane of symmetry. So if we look at this particular molecule, we have a plane of symmetry through the carbon and through the chlorine and the fluorine. Okay. So that puts hydrogens on both sides, and we're cutting through the chlorine and the fluorine. So half chlorine on one side and half chlorine on the other side, and fluorine same way. Now, if we're trying to show that one half of the molecule is a mirror image of the other half. If the molecule has a plane of symmetry, it must be chiral. Um, yeah. Okay. Oh, excuse me. I said chiral. It's achiral. Yeah. Sorry. Yeah. If it has a plane of symmetry, then the molecule is achiral. Because then if we take that molecule and put it up against a mirror, you get an image of the same molecule. Now, what you'll notice is that this plane of symmetry has a fluorine and chlorine, but it's got two hydrogens on it. If the carbon atom has three different attachments to it, and the fourth one is like any one of the other thirds, then your molecule is achiral. Okay. And that's what we call the chiral center. And molecules can have multiple chiral centers. Everywhere you have a carbon, well, actually, it goes beyond that, but let's keep it simple. Carbons, wherever you have a carbon, if you have four different attached substituents, then you have a chiral center. Now, the whole molecule may not be chiral, but you do have the chiral centers. Because if we have a bigger molecule and you draw a plane of symmetry and you get a mirror image on one side and the other, then I think what you get there is a meso compound. We won't go there yet. So this molecule would then be asymmetric. This chiral center requires four different substituents in order to be a chiral center. Okay. What happens if we switch any two of these components? So if we switch W and X, now X is on top and W is on the bottom. If we rotate, right? If we rotate around that, let's see, if we put the W on top where it was at the beginning, then what does that do to the rest of the molecule? Well, the Z is toward the back, the Y is toward the front, but they're on opposite sides. Exchanging any two substituents attached to a chiral center will give you a configuration that is opposite to it. So if we said, okay, we switch W and X, right, around that chiral center, that gives you a different configuration. But if at the same time we switch Y and Z, then that brings us back to the original molecule. Okay. Chiral centers. Our original molecule had a chiral center in it, right, with bromine, fluorine, chlorine, and hydrogen. How about this one? Right, if we look at that one, right, what does it have attached to it? It is a methyl group, an ethyl group, and a propyl group, and a hydrogen, right? We don't show the hydrogens. It's got four different groups on it. So that carbon, let's see, if we start from the left, 1, 2, 3, 4, 5. Oh, methylhexane. 1, 2, 3, 4, 5, 6. On the third carbon, that carbon is a chiral center. Right? Are there any other chiral centers there? No. Because they either have three hydrogens or two hydrogens attached to each one. And all the other groups are different. How about this trans 1,2-dichlorocyclopropane that we looked at a little earlier? All right. Now it gets kind of tricky when you look at cyclic compounds. So you have to say, all right, let's take this one for example. Go. And we have this one coming out. And this one going in. Okay. And we want to look at each one of these, whether it's a chiral center. All right. So if we go to this one, how many hydrogens do we have? Well, we've got one hydrogen here. We've got one hydrogen there. That gives us 4 bonds to that carbon. Okay. Now the question is, do we have 4 different groups attached to that one? Well, you go this hydrogen, that chlorine, and then we go from here. We have 1 carbon, 2 carbons, and these groups, 1, 2. So that's 2 carbons on this side, a hydrogen on that side, chlorine on that side, and on this side we have a carbon with different attachments to this carbon, right? So we went from this carbon, which only has 2 hydrogens, to this carbon, which has this group on it. But if we go this direction, the first carbon we come to has those groups on it. That's a different connectivity. So this one is chiral. And similarly, if we go down here, that one is also chiral. So this molecule has 2 chiral centers. And oh, they're okay. They're using planes of symmetry. Well, that's fine. So 2 halves of the ring are different. So if we look at this one, and if we're going to use planes of symmetry, that means this carbon has to be in the plane. So we would have to go here and say, what does this side look like? It's different than that side. If we go from here, look that, those 2 sides are different. So that gives us actually no planes of symmetry. Okay. If it had plane of symmetry, it would be achiral. But since it doesn't have a plane of symmetry on either carbon, then these 2 are chiral centers. What if we went to this carbon and drew a plane of symmetry? That side looks like this side, doesn't it? So that carbon is not chiral using plane of symmetry, but I think it's easier to use. It's got 2 hydrogens, so it's not chiral. Okay. Bisect the angle made by the 2 bonds. Okay. Evaluate the 2 halves. All right, we did that already. How about this one? Now, in this case, we're not using carbon. We're saying, is that nitrogen a chiral center? So what type of, I like to, whenever nitrogen is involved, I like to look at the possibilities. What does nitrogen usually do? Well, if it's all hydrogens, right, it would be a hydrogen in the back, and it would be, say, 2 hydrogens in the front. And it would form this pyramid on the bottom with like that. Okay. So what could we do? Well, we could substitute for one of these, we could substitute a methyl group. For another one, we could substitute an ethyl group. Right. That takes care of the top and this one sticking out. And then if we go in the back, we could substitute a phenyl group. Right. And then since we've got these 2 lone pairs, we can form another bond with a propyl group. So that would be a, lost the terminology. We talked about it last time. Where nitrogen provides both the electrons for the bond. What type of bond is that? I hate it when that happens. Okay, it'll come to me later. And then on this one, we form the propyl group. But that gives us plus formal charge for the nitrogen. Okay, this is called a quaternary ammonium, right? Ammonium is like this, right? With a plus charge. That's our polyatomic ion, right? We just take that plus charge and substitute different groups for that hydrogen. And that's a quaternary ammonium. A lot of cleaning compounds are quaternary ammonium. Right? We've got one in my lab called call it blank brain. Anyway, you know that if you use ammonia to clean, it's very good cleaning, but the fumes are noxious, and you don't want to mix it with chlorine bleach either. It produces a, was it phosgene? Yeah. So these compounds were developed to be less noxious, the quaternary ammonium, and they clean almost as well as ammonia. Okay, this is a chiral center. It has four different groups attached to that nitrogen. So we can get a mirror image of that one. That's a chiral center. One strict rule. Molecule that has exactly one chiral center must be chiral. Yep. Well, that makes sense. There's nothing to compete with it. With that chiral center, the whole molecule is beholden to that chirality. Oh, here's our meso compounds. Okay. So a molecule that has two chiral centers could be chiral or achiral. The molecule is meso if it contains at least two chiral centers but has a plane of symmetry that makes it achiral overall. So if we look at the one on the left, if we draw a plane of symmetry through that achiral carbon, then we get non-superimposable mirror images. But if we draw a plane of symmetry through the cis molecule, then we get mirror images that are superimposable. That's a meso compound. That's achiral. It still has two chiral centers, but the way I think of it is they cancel each other out. So sometimes instead of cis, if we have established that it's an achiral molecule, we'll put meso in there. That gives you a little bit more information. Okay, determine whether molecules A and B are meso. Well, based upon what we've seen so far, is B is chiral molecule and A is meso. Yep. Okay. All right. So nomenclature. Let's see. We're going to have, let's see, we have nomenclature. We have inner chapters for next ones. Chapter. No. Well, we have inner chapter, probably have inner chapter C, but I'm skipping that. No, there it is, inner chapter C, okay. Molecular orbitals, and then we have inner chapter D as another nomenclature. Okay, so we've embedded nomenclature into this chapter. And this is the RS designations for configurations around stereocenters. Once you've established your stereo center, then we want to say in absolute terms, what is the chirality of that center? And this was developed so that we can be unambiguous in our naming convention. All right, the RS configuration. R stands for rectus, is Latin, I guess. And S stands for sinister. So we look at the chiral carbon and we say, we establish by rules what is the priority of all the attached groups to that carbon. And there are rules to go with it. And then we say, all right, if we follow those by priority, if we follow them from lowest to highest priority, or is it highest to lowest? Highest to lowest. First priority, second priority, third priority. Then if we go to the right, it's called rectus. This is R to the right, like that. If we circulate to the left, it's sinister. And that's easy for me to remember because leftists, Democrats, are sinister. Okay. And by the way, Leah has some good videos on this RS configuration too. Okay, so we're just showing examples here of what it looks like. If we don't consider the chirality, then we would leave off that S and R prefix. And then you would just name the molecule according to our zigzag as 6-bromo-1,2,3-trichlorohexane. Right. We've learned that already. Then if you've established chiral centers, you take each one of those chiral centers and you say from numbering 1, 2, 3, right? The first one is 2 and it's sinister. And the third one is 3 is rectus. Now we have to get the rules to determine. And you can see from the way that the dash wedge is written that in the right-hand side, the top chlorine is going back into it rather than out, and the bottom chlorine is going out instead of back in. So what we've done is we've changed the configuration around that each one of those carbons so that if you do that, then the first one is SR and the second one is RS. Okay, so now we need rules. This is the Kahn-Ingold prelog system. I assume that these are 3 guys that proposed the priorities. CIP, Kahn-Ingold prelog, CIP system. Okay. You assign priorities. You're going to only have 4 substituents attached to that carbon, the chiral carbon, 4 substituents, and they all have to be different. And then you have to decide which one is highest or lowest or highest priority. Orient the molecule so that the lowest priority points to the back. So we would take our molecule and rotate that carbon so that one of them, the lowest priority, points back. And very often that's hydrogen. The first rule is atomic number. Highest priority is the highest atomic number. So if we had fluorine, chlorine, bromine, bromine would be the highest priority. Chlorine would be the second. Fluorine would be the third. And then the one in the back is the lowest priority, and it doesn't count. Because we only care if we have this as our axis, then we're moving this way or that way. Okay? So now we need the rules. The higher atomic number receives the highest priority. If two atoms are isotopes of the same element, say you have, let's see, what's the proton is protium, would be just one proton in the hydrogen. Deuterium would have a neutron. Tritium would have two neutrons. In that case, if they're the isotopes of the same element, then the higher atomic mass receives the higher priority. So deuterium, if we had all three of them there, then tritium would be the highest priority, deuterium next, and hydrogen would be the third. That wouldn't work though, because then we'd have two hydrogens. Right? So I have to think of an example. If there are ties, right, and you work your way out, say, well, let's use our earlier example. Let's see, this is say fluorine and then chlorine and then bromine. Okay. So just number your priorities. This would be the lowest priority. This would be the highest priority. And like that. Then we want to rotate the molecule so hydrogen's in the back. And then we go, all right, what does that do? Well, if we move hydrogen to the back, these being in the same plane, that would move fluorine to the back. And that would bring chlorine and bromine out. So now that we have hydrogen in the back, we could go 1, 2, 3. This is sinister. If we had more attachments out here, like on our quaternary ammonium compound, then we would, and if we had a tie, say we had a carbon here and a carbon here, right? That would be achiral, unless we had like that on this side, and this was H2 and then CH3 on this side. If these are the same, then you move to the next one and compare their atomic numbers. This is a higher atomic number than that one. So now this one would be 2, and this one would be 3. Okay. And then we would go 1, 2, 3. That would be rectus. Okay. Compare the second atoms. Okay, we've done that. Compare the second atoms for priority. And if we have to, go to the third atom if the second ones are the same. It's located one additional bond away. Okay. So that's enough rules for now. There are more. So in this case, assign the substituents priorities based on the atoms at the point of attachment. So if we go to, if we take this molecule as written, 6-bromo-1,3-dichlorohexane, do we have a chiral center there? Yes, we do. Because at carbon number 3, we have a chloroethane on the right, and on the left, we have a bromopropane on the left. Those are different substituents, and we have a hydrogen. Okay, so if we draw in the hydrogen in the back, and then we assign our substituents priorities, then we find that chlorine is going to be priority number 1. Okay. Hydrogen is going to be priority 4. Now we have to say, all right, we go to the next carbons, right? We have to break a tie. Go to the next carbon. Still a tie. Go to the next position. Is a carbon and a chlorine. Chlorine wins. Chlorine now is second priority, and the bromine side is third priority. Let's see. Okay. Oh, okay. I left out a part of the rules. The only reason that those two carbons attached to the chiral carbon are the same is because they both have two hydrogens attached to them. That makes them the same. And then if we go out, those carbons have two hydrogens attached to them. Then when we go to the next one, we compare the carbon and the chlorine, right? If we had something else attached, instead of the two hydrogens on one side, had something else attached with a higher priority, then that would break the tie right away. Okay. Let's see. So that's R. We put the hydrogen. Hydrogen is already in the back. We've got it written that way. So now all we have to do is go priority 1, 2, 3, and that's R. And the way we would write that is if there's only one, let's see. If there's only one chiral center in the molecule, then you only have to say the one R. You don't have to say where it is. If there's more than one chiral center, then you have to identify which carbon. Right? We figure that anybody reading this name is going to see only one R in the name. So if they draw the molecule, they can figure out which one's the chiral center. That way we're not redundant. Right? We wouldn't say 1, 2, 3, 3R. That would be redundant. Okay, what do you do if you have a double or a triple bond? An atom that is double bonded to another atom is treated as having two single bonds to that atom. So if we have an ethene group on the end, that's as if we have another carbon attached to each one of those carbons. Okay. For the next one, where we have a double bonded NH, then the nitrogen is as if it's attached to another carbon, and the carbon is as if it's attached to another nitrogen. Okay. If we have a carbon on the end attached to, double bonded to an oxygen, then the carbon is attached to another oxygen, and the oxygen is attached to another carbon. If we have a triple bond, then the carbon on the left, this is B, carbon on the left is attached to two more carbons, carbon on the right is attached to two more carbons. So for each pi bond, we add an atom that it's attached to the one that we're identifying. Right. So what that does is allows us then to establish priorities based upon connectivity. So here we have an example where we've got an ethene on the end of the molecule. Our chiral center is at the number 2 carbon, actually number 3 carbon. Right? Number 3 carbon is chiral. So hydrogen's already in the back, and we have to establish priority. So we go carbon, carbon, carbon. All right, so how are we going to break that tie? Well, the double bonded carbon is as if it's bound to another carbon. So that's another carbon and a hydrogen. Whereas the CH3 is bound to 3 hydrogens, right? And the propyl group on the left is bound to 2 hydrogens also. So the priority then is given to the double bonded carbon. That's first priority. Second priority is bonded to a carbon. See that second carbon on the left? It's bound to 2 hydrogens and another carbon. So it wins over the carbon attached to 3 hydrogens. Okay? So now we have our priorities. The one on the far right is 1, one on the left is 2, and the methyl group is 3. And what would that give us? Let's see. 1, 2, 3, that would give us sinister. Okay. When the fourth, the lowest priority, does not point away, the examples we've used so far have the hydrogen pointing toward the back already. So that made it easy. If the fourth priority substituent is pointing forward, then you determine your R and S with it pointing forward, and then just flip it. If the lowest priority is pointing forward and you determine it's R, then when you point it backwards, it becomes S. Okay? I mean, you can try it for yourself and see if it works, but take my word for it. Points away. Okay, if the fourth priority substituent is in the plane of the page, it's in the same plane as the chiral center, then exchange the fourth priority substituent with one of the ones in the back, determine the priorities, then reverse the arrangement. So that's the same rule of thumb for both situations. If, say, hydrogen is your lowest priority, if it's in the front, then determine the R and S and reverse it. If it's in the plane, then swap it with some other substituent so that hydrogen goes to the back. Then determine your R and S and change it. Because remember, if you swap 2, that changes their chirality from R to S. So if we swap it, then to do the RS configuration, then if you put it back, that would flip it. So those are 2 possibilities. And this is the example. Do we need to go through that? No, I didn't think so. That's fairly simple. Okay, if we have mirror images that rapidly interconvert around a single bond rotation, that molecule, if a molecule and its mirror image rapidly interconvert, then the molecule is achiral. So we're talking about conformers. If you have a conformer of one molecule versus the other one, then you don't have a stereocenter. You don't have the molecule's achiral. What if we chair flip? Right? If we have a cis molecule and we chair flip it, actually, that cis 1,2-difluorocyclohexane, if we take the mirror image of that, we still have the fluorine closest to the mirror is axial, and the fluorine furthest away from the mirror is equatorial. So can we produce that by the chair flip? Yeah. In this case, we flipped it, so that made the axial equatorial and the equatorial axial. But if we rotate, then we can superimpose. Yeah, okay. So the chair flip, it may be non-superimposable, until you flip the chair. Yeah. So that's not a chiral molecule. Because you can superimpose either one of those. Okay. This may be where the Haworth projection is very useful. Because the Haworth projections are always cyclic molecules. So if we simplify this chair conformation into a Haworth projection and flatten the hexagon out, we find that with our cis-1,2-dichlorocyclohexane, we have a plane of symmetry if the molecules are cis. If they're trans, then we don't have a plane of symmetry. A plane of symmetry means that they're achiral. If they don't have a plane of symmetry, then it's chiral molecule. How about nitrogen inversion? All right. So we're going to, well, I erased it. We're going to the ammonia analog, where we have three different groups attached to the nitrogen plus its lone pair electrons. And if we, what can happen is this molecule, it's like an umbrella. The molecule can turn inside out like an umbrella in a strong wind. So that nitrogen, that ammonia compound can flip like that. Well, it produces mirror images, but they're not superimposable. So this N-methylethylenamine is potentially a stereocenter. So it's possibly chiral. Well, let's see. Do we have a chiral molecule? The problem is the end conversion is so rapid that this molecule is achiral. Its nitrogen atom is not a stereocenter. Well, it should be fairly simple to say this molecule is not a stereocenter because it only has 3 substituents. Right? That lone pair doesn't count. And the other problem is that it flips back and forth so fast that you can't separate them anyway. Even though that they're mirror images of each other and they're not superimposable, they're still not chiral. Let's see. All right, I'm going to skip that. It talks about hybridizations of the orbitals. Right, this is an sp3 hybrid. And it goes through an unhybridized p orbital sp2 hybridization and then back to an sp3 when it flips over to the other side. I don't see what that has to do with our discussion, actually. Okay. That whole part of the chapter was talking about enantiomers, non-superimposable stereoisomers. Now, what's a diastereomer? Oh. A diastereomer is a stereoisomer that is not a mirror image of the other one. Okay. So we have the same connectivity for this example molecule, the dichloroethene is the same connectivity. Chlorine on the 1 carbon and the chlorine on the 2 carbon. But with the double bond there, now we have the possibility for a cis or a trans conformation. They are not superimposable. They are stereoisomers, right? Because they're connected to the same atoms, but they're not superimposable. So these are diastereomers rather than enantiomers. Okay. So we need a convention here that can also be applied to these unambiguously. Whereas we have the Coningo prelogue for molecules with stereocenters. Now, if we've got a double bond in there, right, we only have 3 attachments to the carbon. We can't use that set of rules for this type of molecule. So this is the ZE system. And these letters represent German words. I'm not sure what they are. Are they on another slide? ZE, maybe in your textbook. Oh, Z Zusammen is Z, and you found it?
Yeah, ENTGEGEN.
Entgegen. Okay, Zusammen Entgegen. Okay. Okay, here's the way I deal with it. If there's Z to each other, these substituents around the double bond, they're on the same side. Okay, and if they're cis to one another, they're on the opposite side. Okay, then I don't have to learn German. So that's fairly simple. You look at the priorities. Okay, we do use this system for determining priorities. Okay, and you take the 2 highest priorities and say, which side of the double bond are they located on? So they don't have to be the same molecules or substituents. They just have to have the highest priorities, the 2 highest priorities. And if they're on the same side, they're Z. If they're on the opposite sides, then they're E. Okay, so here's an example where we have around that double bond, we have chlorine, methyl group, hydrogen, and ethyl bromine. Well, if we go to the first carbon, then the highest priority is chlorine. The methyl group is higher priority than hydrogen, but the ethyl bromine, the ethyl bromo substituent, has its second carbon. Let's see. This first carbon has 2 hydrogens and a carbon. This carbon has 3 hydrogens. So this is higher priority than that one. So these are the 2 high priorities. They're on opposite. Oh, wait a minute. Hold on a second. Higher priority than, okay. Okay. I almost got confused again. All right. Okay. Here we go. We've got these attached groups, A, B, C, and D. We look at these guys. Compare the priority between these 2. Okay. In this case, in our example, this one's a higher priority than that one. Yeah, this is a higher priority than that one. So this one, I'll just make that one a prime. On the other side, this is a higher priority than that one. And these 2 higher priorities are on the same side, so they're Z. If we put the chlorine on this side, then this higher priority would be over here. And that higher priority would be over there. They would be on opposite sides. That's E. Okay, so we actually do 2 comparisons. We compare these 2, and then we compare those 2. And this is higher for that one. This is higher for that one. Then we compare them for the Z or the E. Okay. I confused myself. Did I unconfuse you? Okay. Yeah, yeah,
I think so.
okay. So what if we have no double bonds? The ring structure, the double bond, what it does is it stops the rotation. Right? So these guys do have a fixed position in relation to the other substituents. Also, ring structures do that also. So, okay, we're going back to the SR arrangement. So if we have, let's see, diastereomers around this cyclopentane, 1 bromo, 3 chloro. All right. The one on the left is cis and the one on the right is trans. So if the two isomers are related by reversing the configuration of some, but not all chiral centers, then the two molecules are diastereomers of each. Okay. So if we say on the, let's see, what are the possibilities here? What other possible arrangements could we have in this Haworth projection? We could have the bromine and the chlorine on the other side, to the left. And those would be enantiomers. Or on the right, we could flip them, and those would be enantiomers, those two on the right. But if we take the chlorine, hold the bromine where it is, put the chlorine down, or if we hold the chlorine up and put the bromine down, we've got diastereomers. Okay. Now, I'll say again, knowing the difference between enantiomers and diastereomers has a bearing not just on their reactivity, how they react in with other molecules, is if you have a mixture in a reaction that gives you a mixture of these, if the mixture is of enantiomers, you're going to have a difficult time separating them. But if they're diastereomers, the separation is easy. And let's look at it chromatographically. If they're diastereomers, they're going to behave radically different as they attach and release from the stationary phase and move through your column. If they're enantiomers, their affinity to the stationary phase is going to be exactly the same. Unless, there may be a slide on this, but I'll introduce it now. If you have enantiomers in a mixture, you want to separate them chromatographically, then the stationary phase must be chiral also. If the stationary phase is chiral for one arrangement, it's not a mixture of chirality, it's one chiral center only, then you can separate your enantiomers chromatographically. All right. 1-chloro-2,3-dimethyl-cyclopentane. Draw one of its diastereomers. Okay. All we have to do to draw a diastereomer of this one is decide, all right, where are the chiral centers? Is the attached to chlorine? Well, I should say, no, this molecule could be, all it needs is a difference in position for one of the carbons. I would pick the middle and say, make that methyl group, put it back. Let's see, how many chiral centers are there? All right, well, there are 3. Right, if we start with the bottom one and we go, all right, first thing we come to on the right-hand side is a carbon methyl group. pointed out. And the first one we come to the left-hand side is a non-chiral carbon and the second non-chiral carbon. So there you have a stereocenter. Do the same thing for the top one. You end up with a chiral center. How about the middle one? Well, the middle one, if you go to the left, you have a carbon attached to a chlorine. If you go to the right, you have a carbon attached to a methyl group. So that's different. So we do have 3 stereocenters there, right? All we have to do is reverse the configuration at 1 or 2 chiral centers, but not all of them. Right? If you flip all of them, then you have an enantiomer. But if you flip 1 or 2 of them, you have a diastereomer. So it looks like, what did we flip? We flipped 2 of them. All right, if we flip the top one, we get the one on the left. If we flip the top one and the one on the right, we get the one on the right. Those are 2 possible diastereomers. If we flipped all 3 of them, we get an enantiomer. Okay. Here's where we can turn our heads around 3 times. Drawing all possible stereoisomers of a molecule with chiral centers. Each time you add a chiral center, you can double the number of isomers. So the maximum number, this is not the actual number, the maximum number of configurations for your isomers would be the number of chiral centers as the power of 2. Okay, so that cyclic molecule we had before, the maximum number of isomers for that one would be 2 to the 3rd power, or 8. Okay. And it depends on the symmetry of the molecule as to whether the molecule is chiral or if it may actually be meso, which would make it achiral. Okay. The easiest step, find all your chiral centers. Identify the chiral centers. Then draw your first structure by specifying the configuration at every chiral center. Use a dash wedge notation to specify each configuration. For the first structure, the choice of configuration doesn't matter. It's your starting point. So you just pick one. Make them all go out, or all go in. Then draw the second structure by reversing the configuration at 1 chiral center only. Then draw the next 2 structures by reversing the configuration at the chiral center. So here's where we're doing our decision, they could call it a decision tree, but if you take 1 chiral center and then you drew 2 possibilities, and then you take this one and do 2 more possibilities, and depending on how many you have, you would keep doing that, and then you would go back and do this, and then you go back and do that. You could keep bifurcating because it's either in or out, right? And do all those possibles, and you know that the maximum number you can have here is 2 to the n power. So you know when to stop, right? This would be 1, 2, 3, 4, 5, 6, 7, 8. That would be 3 chiral centers for this molecule, and you could draw 8 possibles. It's kind of like elementary reactions. Right? When we were talking about kinetics. If you want to determine the elementary steps for a reaction, then you just propose, right? You spitball, you brainstorm, and then you go in and start whacking away the ones that don't make any sense. So that's kind of like what we're doing here. Continue this pattern until you have all the possible structures. Then look for any redundant structures and omit them. So how about this one? It's got 3 chiral centers, and that means 8 possible isomers. So the first one, they did what I would have done, all out. Right? Then we changed the first one. Right? So that gives us our first 2. Then we take A and send B back. And we take A and then we take B and send the second one back. Then we take C at the top and we flip the third one. Well, that's not right. No, that's not what we're doing. A goes to E with that flip. All right. That's not logical. They're not doing it the way I would have with this bifurcating. But you should end up with 8 isomers. 1, 2, 3, 4, 5, 6, 7, 8. And these are unique. Each one of these is unique. All right. Here's the one that gives me a headache. Howarth. Now this projection is Fisher. Fisher projections. Emil Fisher was working with carbohydrates, sugars in particular. And he was getting tired of drawing dash wedge configurations for his molecules, because these sugars can have, 4, 5, 6, 7, 8, 10, they can be monsters. So he devised this simplified version. And it's easy to understand when you've only got one chiral center, one carbon chiral center. So what we're looking at here is often referred to as the bow tie, because the way he draws it puts the carbon in the middle, and then the 2 lines, vertical lines, go back, and the 2 horizontal lines come out. Now that's not a problem with only one carbon. Right? But when you get to the second carbon, if we exchange Y for another carbon, then we still have to go out and back. So what it looks like to me is, as you do that, you're taking your molecule and you're going around like this. That's the bow tie. I forget the lady's name now. Leah Persai. She's got a couple of good videos. One of them is she does it one way, and the second one is better. So if you're looking at one of her videos for converting a Fisher to a dash wedge, or a dash wedge to a Fisher, and within the first 3 or 4 minutes, if she doesn't say, I used to do it this way and now this is a new way, then go find the other one. Okay, so that's for a simple 1 carbon. Oh, okay, sorry. Oh, well, we're out of time. And we're not going to have time for our lab.
Yeah. How long are the chapter lines?
Well, the inner chapters are usually shorter.
Yeah.
might be able to do the. Oh, wait a minute, proton transfer, arrow pushing. We might be able to do it on Wednesday instead. So if we run out of time, we'll do the lab on Wednesday. I'll just leave it set up. And that'd be great for you too.
Yes, that would be awesome. See you guys.
Wait a minute. 104. What's that? Wednesday's 10th. I'm looking at my other course, which has a lab. We're gonna walk over each other. If I can leave it, I think I can leave it set up. Because it's a small class. We can just move to a different bench. There. No, we don't have light. Okay, we're good. Okay, so let's try to progress to. Okay. One of the advantages to the Fisher projection is you can quickly decide if two molecules are stereoisomers of each other. If we say the Fisher is this one with XYZ, WXYZ in the clockwise, and we draw that dash wedge, and then we rotate it. If we rotate it, now the let's see, we're going to rotate it 90 degrees. Yeah, W is on the right, then Z is on the top, and then so okay, so we did that. I'd rather use something else. How about if we do this? And let's put I don't know, chlorine, hydrogen, methyl group, and chlorine. So now we know this is a chiral center. These are coming out, those are going back. If we rotate it 90 degrees, now we've got hydrogen on the top, fluorine on the bottom, methyl group on the right, and chlorine over here. Okay, so we rotated it. But when you rotate a Fisher, now this one, which was out, is supposed to be going back. Right? So initially it was like this. And now it's like this. Okay. So this was back, now it's out. What we've done by rotating that is actually produced a different molecule using the Fisher projection. So whenever you rotate by 90 degrees, a Fisher projection, you get a stereoisomer, a non-superimposable stereoisomer of your original molecule. Now, what would happen if we went 180 degrees? I think you got the same molecule. Okay, so here's 1, 2, 3, 4, 5, 6. Okay, these are hexoses. A hexose is a 6-carbon sugar. And these are all aldoses, hexoaldose. Glucose is in the middle, and we're still, the verticals are back and horizontals are forward. Now, in order to make that actually happen in real 3-dimensional space, we would have to curve the molecule like this. So what this tells us quickly is that the glucose, the D-glucose and the L-glucose are enantiomers. You see that the hydroxyls are opposite to each other in each case. And these molecules have 1, 2, 3, 4 chiral centers. The top carbonyl group can't be a chiral center, and the bottom CH2OH group can't be chiral either because it has 2 hydrogens. So this quickly shows us that D-glucose and L-glucose are enantiomers, and allose and glucose are diastereomers. Okay? I think that's one of the big advantages of the Fisher projection. That's why Fisher did it. But if you want to convert back to a dash wedge, it takes some doing. I think most videos that you see in these conversions are going to be such that you're going to say, all right, for each stereo center, is it R or is it S? And once you have the RS configuration, then it's easier to convert into the dash wedge. Well, there we go. He was reading my mind. Okay, since vertical bonds point away from you and horizontal bonds towards you, then we want to get the fourth priority. Or look at it this way. All right, we've got this situation, and we've established priorities first. Right? First priority is the oxygen with the hydrogen on it. Let's see. Second priority is okay. Oh yeah. Right. Attached to that central chiral carbon, oxygen is first because it has a higher atomic number. And the next attachment up there is carbon, not the oxygen. The arrow is pointing to oxygen, but actually you look at the carbon of the carbonyl group. It's a lower priority than oxygen. And then the third priority is another carbon, but it has, rather than 2 oxygens attached to it, remember if you have a double bond, you have 2 oxygens. Then that carbon is attached to 2 hydrogens and an oxygen. So that is the third priority, and hydrogen, of course, is always the lowest. So with this arrangement, H is pointing out. But if we take 1, 2, 3, it goes sinister. Then if you reverse that, because now we need hydrogen to go back, reverse it, then you get R. Okay, so how about we've got what? 1, 2, 3 stereocenters in this molecule. And we want to do converted to Fisher projection. Carbon 1 is part of the carboxylic acid group. And C5 is part of the CH2OH group. So neither one of those is stereocenter. So all that's left to do is placing hydrogens and hydroxyls around the 3 central carbons. And next, wait a minute. Oh, it's okay. It's doing that, isn't it? Yeah, it's doing that. All right. So, I don't know if this is very helpful. Let's try to do it ourselves. All right. All right. We've got carbon 2, carbon 3, and carbon 4. Carbon 2, carbon 3, and carbon 4. So we want to do what R and S around those carbons. All right. If we look at the carbon 2, what's the priority? Right, is it clockwise or counterclockwise? All right, if we go from that carbon, oxygen is the highest priority. Then we have a carbon attached to an oxygen is and a hydrogen attached to an oxygen. Carbon 2, that carbon, okay, number 3 carbon. Number 3 carbon is has a oh, we're comparing 1 and 3. That's right, we're comparing 1 and 3. Carbon 1 and carbon 3. So carbon 1 has 3 oxygens, right? Carbon 1 has 3 oxygens. Carbon 3 has a hydrogen, a carbon, and an oxygen. Right? So carbon 1 wins. Right? So we have the top, the left, and the right in that order. But is hydrogen in the back? Or is hydrogen forward? Well, the 2 bonds on the left or the right are in the plane. So if the hydroxyl is forward, the hydrogen must be back, right? Okay, so it's back. That's the way it should be. So we would go top, left, right. It's sinister, right? So number 2 is S. Okay. How about the next one? Carbon 3. Okay. Carbon 3 is attached to carbon on the right, carbon on the left, oxygen on the bottom. So the carbon 3 has that hydroxyl is priority number 1. Then the 2 carbons, we have to break a tie. Right? They're each attached to a hydrogen and an oxygen. So we got to go out and break another tie. So the one carbon 2 on the left is the next priority. So it goes 1, 2. Well, wait a minute. Is the hydrogen in the back? Yeah, because the hydroxyl's front. All right, so it's 1, 2, 3. That's breakfast. Okay. Then the last one. We have hydroxyl is highest priority. Then we have 2 carbons to compare. The one on the left is attached to an oxygen. The one on the right is attached to an oxygen. So we go out, and that means the one on the left is higher priority because we can't go any further than hydrogen. So the one on the left is higher priority. So we go 1, 2, 3 is sinister, but hydrogen's in the front. All right, so we have to flip it. So this one's R. Okay, so now that we've determined that, it looks to me like the hydroxyls for S are always on the left and the R's are always on the right. I believe that's the case. So for this one, we would get the sinisters are on the left, which is good because that's mine. Yeah. And good guys are on the right. Oh, and then we have to draw in the carboxylic acid group and the achiral alcohol group. Okay. We have 2 stereocenters here. Oh, we want to go backwards. Want to go backwards. All right. Fortunately, they only gave us 2 carbons to do it this one. All right. So let's look at at this molecule, CN, that's achiral, because this is a triple bond to the nitrogen. That's a nitrile group. And this is CH2OH, it's not chiral. So these are chiral. And we're given OHs on this side and OH on that side. So this is going to be R, this is going to be S. All right, if we look at it this way, if we turn it this way, like that. OH on this side and CN on this side. Then we have these chiral centers. All right. So we're going to come out with a wedge here and a dash here. And let's see, we put the wedge over here. Yeah. Wedge on this side and dash on that side. So if this is 2 and this is 3. So this is 2 and this is 3. So if this is rectus, then we need to go highest priority to the right. So the highest priority here is oxygen. So this is highest priority. And then from here, we have to compare carbon is hydrogen. And here we have a carbon, there we have a carbon. This is attached to an oxygen and a carbon, and this one's attached to 3 nitrogens. Oxygen is higher priority, so this one is higher priority. This is 2. And this is 3. Right. So we go 1, 2, 3 this way. But wait a minute, we already did that part. So we want to translate that over to this one. Which one would give us a rectus around this one? If this is hydrogen in the back, and this was OH, then we would go to this one. So this one is OH, that one's hydrogen, like that. Okay? Okay, this one, we have, this is highest priority. And then this one has 2 hydrogens attached to the carbon. This one has an oxygen attached to the carbon. So this is 1, 2, 3, 2, 3. But this hydrogen is out. And this is sinister. 1, 2, 3 that way. So we need to go the other direction. So we need hydroxyl would be, let's see, sinister, we would go to the left. If we put hydrogen in the back, that would go the wrong direction. Like that. I think that's correct. Right, let's see. Nope. It didn't like it. Okay. I got it wrong. Okay. The top of the Fisher projection will become the left end of the zigzag. Yes. Dash bond because OH appears on the right side. Dash bond because OH appears on the left side. So they're alternating. If they alternate, then this is dash, 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 if we have more. Okay, so this is, excuse me. This is OH.
Let's get the word off the block.
Oh, you gotta go?
Yeah.
Oh, okay.
It's It's over 15 minutes.
How we doing on slides?
Like 8. That's all messed up.
Are we getting there? Okay, well, it's recorded.
Yeah.
We'll watch it later.
Last
These-
in 15 minutes, right?
Huh?
Last in
In 15 minutes, yeah. I don't mind admitting that these Fisher projections always give me a headache.
So Wednesday exam.
Yes,
The
Yeah.
next quiz is on. You're taking that chapter C.
okay, Wednesday. Exam 2. And then we're gonna look at chapter 6 and arrow pushing. Yeah. Chapter 6 is proton transfer reaction. That's the first reaction we're gonna encounter. And that's it. That's all we're gonna do.
The next quiz will be the arrow pushing.
Yes. That'll be on the following week from today.
All right, I'll see you Wednesday. We're gonna do live Wednesday too, right?
Yes. Okay. I'm gonna have to brush up on these things. If I can't explain them to you, I mean, it's not fair for me to expect you to get them. Constitutional, physical and chemical properties. Okay. Constitutional isomers must have different physical and chemical properties. Examples, if you have double bonds and the double bond position changes, then you have a constitutional isomer. Or if you have a straight chain and you have an isomer of that in a ring structure that has different physical and chemical properties. These are structural isomers, constitutional isomers. Yeah. Enantiomers, on the other hand, have identical. They have the same connectivity and they have the same polarities. So that gives them identical physical properties. And they also have the same chemical properties. Okay. All right, here we get, okay. Here we're getting to the possibility of separating enantiomers. In an achiral environment, enantiomers have exactly the same physical and chemical properties. In a chiral environment, they can separate. Diastereomers, though, they're going to be different. They have to have different physical and chemical properties simply because they're not mirror images of each other. Oh, and a perfect example, this 1,2-dichloroethane, if it's cis, it has one type of polarity. If it's trans, it's nonpolar. So you see that in the boiling points. The boiling point of the cis molecule is much higher than it is for the trans. And it also depends, diastereomers can have similar properties, but not exactly the same. Right? Even if they're very close to each other, like the two molecules on the right, their boiling points are different enough so that they could be separated by fractional distillation. Okay, if we want to separate configurational isomers, it's fairly simple. Louis Pasteur did it with a microscope and a pair of tweezers. That was the first separation of isomers. Sodium ammonium tartrate. He was working with the wine producers because they were having trouble with their wines going sour, converting ethanol to acetic acid. So he was helping them try to figure that one out. And he settled on oxidation. They got to keep the oxygen out of them. You got to keep the oxidizers away from them in order to maintain the ethanol content. But in the process, he discovered these crystals of sodium ammonium tartrate. And he noticed under the microscope that they had different shapes to each other, and they looked like they were mirror images of each other. So he went to the trouble of going in tweezers and he separated them each. And then he dissolved them in a solvent. They're probably water soluble. And he determined the optical rotation on each one. And he found that they were exactly opposite by the same magnitude. They rotated light. One of them rotated light so many degrees this way, and the other one this way. And that told him that even though that they had the similar, they had exactly the same chemical and physical properties, that they had this difference. So that was our first introduction to enantiomers. Okay, so how do we separate enantiomers? There are a number of possibilities. You can convert an enantiomer into the diastereomers. Then they can be physically separated. Then when you separate those diastereomers by physical means, usually, then you can regenerate the enantiomers. So you have to pick the chemical conversion that you want to apply to your enantiomers so that it can be easily removed afterwards. That's the trick. That's one way. One way to separate enantiomers. The hard way is Pasteur's way. This is an easier way. Polarization, that's the word I couldn't think of. Polarized light is affected differently with enantiomers. Okay. So if you've ever used shades on your glasses that have polarizing lenses, then you can take them, and on a sunny day, you can do like this. It gets darker, lighter, darker, lighter. Then you know that you've got polarizing lenses, not just dark glasses. So this optical rotation can be measured, and if the light is rotated clockwise, we call it dextrorotary, and if it's counterclockwise, we call it levorotary. So that's where the D and the L prefixes come in. So D-glucose and L-glucose are designated based upon their optical rotation. Now, if you apply D and L to any other of these sugar molecules, it may not have the same stereochemistry. Right? The arrangement of the hydroxyls on the molecule might be different. So this is a practical application. It's an operationally defined designator as D or L. So that's why it's not, if added to the name, it creates a trivial name, right? It's not IUPAC. IUPAC has to be R or S or Z or E. So these are factors that govern the angle of rotation, and that's what alpha stands for, the angle of rotation. You need the standard value for the molecule, and then you need the path length and the concentration. So this is kind of like Beer's law, where you have the amount of light absorbed by a molecule depends on the path length and the concentration of the chromophore. And plus the specific absorptivity. In this case, instead of absorptivity, we use the specific angle of rotation. And enantiomers, that factor, that specific rotation, is equal and opposite for enantiomers. Now, if you have a mixture of enantiomers in exactly equal concentrations, then the optical rotation will be canceled out. Because one will try to rotate it the one way and the other will rotate it the other way, and you'll end up with no optical rotation at all. But if you have an excess of one or the other, then of course you'll get rotation either to the right or the left. And we use this specific rotation for a mixture of enantiomers to determine its purity. Oh, here's the thalidomide story. We don't need to hammer that one anymore. This particular, let's see, which one was it that was the good side and one's the bad side? This enant, it doesn't tell us. Where is the chiral center? Chiral center. I think it's at that carbon on the 6-membered ring over here. That carbon right there. I think that's the chiral center that we're interested in. Okay. These are examples of chiral centers in biomolecules, right? The amino acid, every amino acid, the alpha carbon is a chiral center. Everyone. That's a good rule to go by. Glucose or the aldoses, they have the number of carbons -2 chiral centers, right? The terminal carbons are not chiral. Now these are the aldoses. The ketoses are different because we move the keto group inward, so they should be reduced in the number of chiral centers, I think. This nitrogenous base for DNA, your chiral centers are going to be on the sugar part of the molecule. This is deoxyribose right here for DNA, and it has 3 chiral centers. Testosterone, let's see, how many does it have? 1, 2, 3, 4, 5, 6. So my guess is that the various isomers of testosterone have different hormonal activities. Okay. I already mentioned this one. The D sugars rotate clockwise and the L's counterclockwise. D versus L. Okay, so this is the simplest sugar, glyceraldehyde, D-glyceraldehyde. And the reason we're introducing this one is because the isomers, the chiral center, yeah, the chiral center nearest the keto, the aldose group at the end is the one that we focus on for the D versus L. Oh, keep going. Amino acids, you can have D's and L's for amino acids. These are a little less problematic because there's only one chiral center. That's the alpha carbon. It's the one we focus on. I can imagine that the side groups, the R groups, could have chirality to them also. Let's see. All right, families of. All right, we're not going to hammer this one too hard because you wouldn't need to know this unless you were going to do biochemistry. Yeah. Okay, so I made a mistake. The chiral carbon in sugars is the closest one to the terminal hydroxyl group. So this CH2OH is the end that we focus on. And the next carbon up, the first chiral carbon from that group, is the one that determines D or L. Now, it's got a plus and a minus in there, and I think those are also separate determinants from the D and the L.